Hello student, in this video I am going to explain the Bernoulli distribution. First we see the concept of Bernoulli distribution and then definition. To understand the Bernoulli distribution, we start with the example. Consider an experiment of tossing a coin. Then define x equal to 1 if head turns up and x equal to 0 if tail turns up. Then let p is equal to probability of getting head and q is equal to probability of getting tail. Thus the p plus q is equal to 1. Then this implies that q is equal to 1 minus p and p lies between 0 and 1. Then if p is equal to q, if p is equal to q is equal to 1/2, okay, then the coin is unbiased. Means if coin is unbiased, in that case p is equal to q is equal to 1/2, then the probability mass function can be expressed as follows. Probability of x equal to small x, which is equal to p raised to x into q raised to 1 minus x. Here x takes values 0, 1, 0, otherwise. This is the probability mass function of Bernoulli distribution or Bernoulli random variable. If we substitute x equal to 0 in this PMF, then we get the probability of failure. Means what? If x equal to 0, if x equal to 1, then we have a success, and if x equal to 0, then we have a failures. Okay, then if we put x equal to 0 in the PMF, then we get probability of failure, that is q. And if x equal to 1, then we have probability of success. Means here p is the probability of success and q is the probability of failure. Bernoulli experiment, or it is also called as the Bernoulli trials, has only two outcomes, out of which one is success and other is failure. The probability of success is p and probability of failure is q. The total probability p plus q is equal to 1, and the probability mass function of Bernoulli random variable is p raised to x into q raised to 1 minus x. Here x takes values 0, 1. From this we see that if substitute x equal to 0, then we get probability of failure, and if we put x equal to 1, then we get the probability of success. Now the some real life situations of Bernoulli distributions are: the sex of newborn baby recorded in a hospital, then the items in a consignment are classified as defective and non-defective, the student appears for the examination, then he passes or fails. These are the some examples of Bernoulli trials or Bernoulli distributions. Now we see the moments of Bernoulli distributions. Moments of Bernoulli distribution. Bernoulli distribution. If x follows Bernoulli distribution with parameters 1p, then its PMF is given by, then probability of x equal to small x, which is equal to p raised to x into q raised to 1 minus x. Here x takes values 0 and 1, 0 otherwise. Now first we find the expected value of the random variable x, which is called as the mean of the Bernoulli distribution. Expectation of x is equal to mu1 dash, which is equal to mean, which is equal to summation of xi into probability of x equal to xi summation over I running from 0 to 1. Therefore expectation of x is equal to summation of xi into p raised to x into q raised to 1 minus x summation over x running from 0 to 1. Now this can be expressed as put x equal to 0, then we have a value 0, plus now put x equal to 1, then p raised to 1 into q raised to 1 minus 1, which is equal to p. Expected value of x is equal to p, which is the mean of the Bernoulli distribution. Now we find the expectation of x square, which is also called as the second order raw movement, that is mu2 dash, as follows. Mu2 dash is equal to expected value of x square, which is equal to summation of x square into probability of x equal to x summation over x, and which is equal to summation of x square into p raised to x into q raised to 1 minus x summation over x takes values 0 to 1. Now substitute x equal to 0 and x equal to 1 in this summation, which is equal to 0 plus p raised to 0 into q raised to 1 minus 0, plus put x equal to 1, then we have 1 into p raised to 1 into q raised to 1 minus 1, that is 0 plus p into q raised to 0, which is equal to p, that is mu2 dash is equal to p, the second order raw movement, or which is the expected value of the x square. Now we find expectation of x cube. Expected value of x cube is equal to mu3 dash is equal to summation of x cube into probability of x equal to x, which is equal to summation of x cube into p raised to x into q raised to 1 minus x summation over x takes values 0 to 1, again which is equal to put x equal to 0, then we have first term is 0 plus second term put x equal to 1, then 1 into p raised to 1 into q raised to 1 minus 1, that is mu3 dash is equal to p. Then we find out expectation of x raised to 4. Expected value of x raised to 4 is equal to summation of x raised to 4 into probability of x equal to small x summation over x. This is by definition of expectation. Then substitute the probability mass function of Bernoulli distribution here, that is summation of x raised to 4 into p raised to x into q raised to 1 minus x summation over x takes values from 0 to 1, again which is equal to 0 plus p, which is equal to p. Expected value of x raised to 4 is equal to p, which is the mu 4 dash, fourth order raw moment. From this we can conclude that for the Bernoulli distribution all raw moments are equal to p, that is mu r dash is equal to summation of x raised to r into probability of x equal to small x summation over x running from 0 to 1. Here r takes values, this is equal to p. Here r takes values 1, 2, 3, 4, so on. Means all odd order raw moments of Bernoulli distribution are equal to p. Now we find central moments of Bernoulli distribution. Central moments of Bernoulli distribution. Central moments. mu1 is equal to always 0. The first order center moment is equal to 0. Then mu2 is equal to mu2 dash minus mu1 dash square. Now substitute values of mu2 dash and mu1 dash, and we have mu2 dash is equal to p minus mu1 dash is equal to p, that is p square. Now take p common, then we have mu2 is equal to p into in bracket 1 minus p, which is equal to p into q is the mu2, second order central moment of the Bernoulli distribution. Here since p plus q equal to 1, this implies that q is equal to 1 minus p. Okay, mu2 is equal to p into q. Now we find third order central moment of the Bernoulli distribution. mu3 is equal to mu3 dash minus 3 into mu2 dash into mu1 dash plus 2 into mu1 dash raised to 3. This is the third order central moment in terms of raw moments. We know that all the raw moments of Bernoulli distributions. Therefore, mu3 is equal to mu3 dash is equal to p minus 3 into p square plus 2 into p cube. Now take p common, which is equal to p into in bracket 1 minus 3 into p plus 2 into p square, which is equal to p into in bracket 1 minus p minus 2p. This 3p can be written as minus p minus 2p plus 2 into p square. Then we know that 1 minus p is equal to q, which is equal to p into in bracket q minus, now take 2 into p common from these two terms, minus 2 into p into in bracket 1 minus p, okay, and which is equal to p into in bracket q minus 2 into p, and 1 minus p is equal to q. Okay, now take q common from these two terms, then we have p into q into in bracket 1 minus 2 into p. Again this can be written as p into q into in bracket 1 minus p minus p. This 2p can be written as minus p minus p. Then again we know that 1 minus p is equal to q. Then p into q into in bracket q minus p. This is the third order central moments of the Bernoulli distribution. If we substitute p is equal to q is equal to 1/2, then the value of mu3 is equal to 0. See, for p equal to q equal to 1/2, mu3 is equal to 0. Hence we can conclude that if p equal to q equal to 1/2, then the Bernoulli distribution becomes symmetric. If mu3 is equal to 0, then in this case the type of the distribution is the symmetric. Okay, now we see moment generating function of Bernoulli distribution, MGF of Bernoulli distribution. Moment generating function of Bernoulli distribution. Moment generating function in bracket MGF. Okay, by definition of MGF we have mx of t is equal to expected value of e raised to t into x. Then by definition of expectation we have summation of e raised to t into x into probability of x equal to x summation over x. Then substitute here the probability mass function of Bernoulli distribution here. Then mx of t is equal to summation of e raised to t into x into p raised to x into q raised to 1 minus x summation over x. X takes value from 0 to 1. Now put x equal to 0 and x equal to 1 in the above summation. Then we have put x equal to 0, e raised to 0 into p raised to 0 into q raised to 1 minus 0 plus, now put x equal to 1, then e raised to t into p raised to 1 into q raised to 1 minus 1, that is e raised to 0 equal to 1, p raised to 0 is equal to 1, q raised to 1, that is q plus e raised to t into p. Here q raised to 0 is equal to 1. Therefore mgf of Bernoulli distribution is equal to q plus p into e raised to t. This is the moment generating function of Bernoulli distribution. Then we see the distribution of sum of independent and identically distributed Bernoulli random variables. Now sum of distribution of sum of independent and identically distributed Bernoulli random variables. Now see, let yi, here I takes values 1, 2 dash dash n, b n independent Bernoulli random variables with parameter p, that is probability of yi is equal to 1 equal to p, and probability of yi is equal to 0 is equal to q. Here I takes values 1, 2 up to n. Now define x equal to y1 plus y2 plus so on plus yn. The y1, y2, y3, so on yn, these are the Bernoulli random variables. Then x is equal to, this can be written as x is equal to summation of yi summation over I running from 1 to n. Here note that this x counts the number of ones only, that is successes in n independent Bernoulli trials. Now we have to derive the probability of x equal to x. We have to derive the probability of x equal to x, that is we have to calculate the probability of x successes in n trials. Then to derive the probability of x equal to small x, we consider the sequence of particular sequence of 0 and 1s. The particular sequence of 0 and 1s means here 1 1 0 1 1 1 0 0 0 1 1 1 1. This is the particular sequence of 0 and 1s. Means what? Here 1 stands for success and 0 stands for failures. In this sequence there are x successes and remaining n minus x are the failures. In total there are n trials. Then in this sequence 1 occurs x times and 0 occurs n minus x times. Then the probability of this sequence is due to independent. The probability of this sequence is equal to p into p into p into p, then q into q into q into q, again dash dash into q. Here p occurs x times and q occurs n minus x times, and the probability of this sequence is equal to p raised to x into q raised to 1 minus x. Means in n trials there are x successes and remaining n minus x are the failures, and the probability of success is equal to p raised to x into q raised to 1 minus x. However, the successes can occupy x places out of n places in this sequence in nc x ways. nc x ways. Therefore, by using addition principle, we have probability of x equal to small x, which is equal to ncx into p raised to x into q raised to n minus x. Here x takes values 0 1 2 up to n 0 otherwise. This is the probability distribution of sum of independent and identically distributed Bernoulli random variables, and this PMF is the PMF of binomial distribution, that is the sum of independent and identically distributed Bernoulli random variables have binomial distribution with parameters n and p. In binomial distribution, the experiment is repeated n times with probability of success is equal to p and probability of failure is equal to q. Okay, thank you.